Hi, this video will cover section 1.7, transformations of functions. We will be using some types of transformations, such as the vertical and the horizontal shift, or also known as translation. We will be using the reflections. We're going to have two types of reflections across the y-axis and across the x-axis. And also we will use non-rigid transformations to sketch graphs of functions. So we'll do some examples. One more that is not mentioned here, it will be the vertical or horizontal stretching. And sometimes we could have both at the same time. Stretching or shrinking. Okay, so next slide. We have the first one we will address is the shifting of graphs, and the graphs can be shifted upward, like the example that you see here. So the parent function, remember in our previous section we went over the parent function, and so that is f of x equals y squared. I'm sorry, x squared. And the transformation that we have here is going to be we use a different letter than f, so in this case we're calling it h of x, and it's going to be x squared plus 2. So what this means is that it is the shifting of the original graph up 2 units, and we know that it is up because we have a positive 2, but also because the 2 is not affecting the x directly. So if we want to rewrite the equation that we have here, actually we have it down here. So we know that this part right here is the parent function, so we're just replacing the x squared with the name of the function, which in this case is f of x. So we could generalize that vertical translation as having the parent function as you do here, and then adding 2 units. What's happening here is that the 2 units are going to be added to the y coordinate of every single point. So for example, this point was at 0, 0, and after the shifting was completed, the point became 0 for x and 2 for y. So we are going to add 2 to every y coordinate, and only to the y coordinate for this example. We can have some shifting that occurs vertically and horizontally in the same example. Okay, now the next one is a very clear example of a horizontal shifting, and you could see I'm going to highlight the parent function again, which is, we're calling it f of x, and that's the one we have. And I'm going to also use the vertex as the sample point. So the sample here will be 0, 0. And so what's happening here, the point is going to move 2 units to the right. So in this case, we're calling the graph g of x. So g of x will be the same as f of x, or x squared, but shifted 2 units to the right. And so if we want to write g of x in terms of f of x, it will be the same as f of x, the x squared. But in this case, we're not going to add or subtract the 2 outside, well, I shouldn't have the square here. We are just going to put it inside so the parentheses, so it affects the 2 directly. And so that will be the equation. And what that means is exactly what we have here, which is, and actually I should color this one yellow, the parent, which will be here, x minus 2 squared. So you could see how the 2 is affecting the x directly, and that's why it goes inside the parentheses. So why does it move to the right if we have a minus 2? So for all horizontal shifting, we are going to use the counterintuitive idea. So we will be, if we see a negative, and this is only for horizontal shifting, only for horizontal. If we see a minus 2 in the equation like that, we will know that it's moving to the right. And we're going to summarize this in a minute. So the horizontal shifting is counterintuitive. Counterintuitive. So if you see a minus 2 but is in parentheses, that's how we know it's horizontal. So we will, the opposite of the number line, the opposite of what our intuition will tell us, we're going to move to the right. And if we had, let's say, another example like h of x is equal to x plus 2 and then square, then this graph will be f of x but shifted 2 units to the left in this case. So I want you to get used to that, and it's only for horizontal changes, for horizontal shifting. We will say to the left, and if we see a minus, then we will say to the right. So let's move on. And here is the summary of the shifting of graphs. So we have the examples that we did with vertical was moving it up. So you will see a constant that is being added. And for this, we are assuming that c is a positive real number. So if we add a positive number, we will be shifting the graph vertically those many units, whatever c is equal to, up. And if we see a minus that positive constant, it will be those many units down. Now for horizontal shifting, it is counterintuitive for both. So if we see, again, c is just a positive real number. So if we have a minus of that positive real number, we are actually going to move to the right, those many units, c units. And if we have a plus that constant, that positive constant, we're going to move to the left. So what will we do if we had a table or a graph? Well, you can look at the points on the graph or the table by row, and you will know what x and y will be. So the shortcut to what to do for here, you will add c to every y. Here you will subtract the constant from every y. I'm just going to put from y because I don't have enough space. And then for the horizontal shifting, the change is going to take place not on the y, but on the x. And so if we see that, we will again think of the counterintuitive. So the inverse operation of subtraction will be addition. So we will be adding c to the x. And for the one that has a plus here that is actually moving to the left, we will subtract the constant from the x. So again, horizontal changes occur to the x value. And vertical changes are going to occur to the y value, as you can see here. So this is a very useful table. Make sure you have it handy when you do your homework and when you take your quiz and your exam. Okay, so the next two graphs, we have the parent function right here, which is x to the third power. So it's either a cubic function, parent function of cubic functions, or a polynomial of degree 3. And so on the example on the left, we have a -1. So if we look at our table, that -1 is not being subtracted from the x, is actually being subtracted from the x cubed. So it's like we have something similar to f of x, the whole function, the parent, this is the parent. So we have that -1. So that tells me that it is a vertical shift. And it's going to be of 1 unit down. And for our other problem, we actually have two types of shifting. We have horizontal and vertical. So let's go ahead and address the one at a time. So let's see, h of x is gonna be equal to, this is like we have f of x plus 2 and then a plus 1. So it's pretty obvious that the plus 1 in this case is causing the vertical shifting. So this is going to be 1 unit up. And this plus 2, remember, is counterintuitive. And we know it's horizontal because it is being added directly to the x inside the parentheses, and then outside the parentheses we have the type of function, the third power, the cubic function. So this is horizontal. That's how we distinguish from vertical and horizontal. So it's gonna be 2 units. And remember, if you see a plus, we actually we want to move to the left. Okay, so what does this mean? So for example, on the parent function, we could have the following points. Let's say, let's use 2, -2. So we could have the point -2, comma, -2 to the third power will be -8. And then we could also have the point +2 and +8. So what this function will have, g of x, we're going to add 1 unit to the y coordinate because we're making a vertical shift. And so this point will be -2, comma, and here we will have -8 plus 1. So that is actually -7. And for the other point, we're going to have +2 for the x, nothing happens, but we just need to add 1 unit to the y, so that will be a 9. Now for the next, for the example on the right side, again, we do have f of x, and I'm going to just use the same points from the parent function. Let's draw them here. So we're going to have the same points -2 comma -8, and then we're going to have 2 comma +8. So here for h of x, what's happening is we're going to add 1 to y, and then we're also gonna, what will we do here? We're moving to the left, so we're going to subtract 2 from x. So the points are gonna look this way. So to the x, to the -2, we're gonna subtract 2, and then comma, and to the y, which is a -8, we're going to add 1. And so this point will happen to be -4, comma, -7. Okay, and for the next point, again, we're going to subtract 2. Oh, that was actually a +2 originally from here. So we're going to subtract 2 for the horizontal shift, and then to 8, we're going to add 1 because that was the vertical shift. So then this point will become 0, comma 9. And so those are 2 points that you could look at or plot to help you with your transformation. Now, if you are not so sure, you're welcome to use your graphing calculator, or you could go to Desmos. Desmos is a free software, in case you didn't know, and that is the website, actually, right here. That is the website, desmos.com, and what you could do is just start using the graphing calculator. So we're going to graph the same equations we had, and we could actually graph them all at the same time, so it's pretty convenient. So we're going to put first y equals to x to the 3rd power. So that will be the cubic parent function. And then for the second equation, I'm going to check what it was again. X cubed minus 1. Okay, and I just realized that I made a mistake. So here for part A, we have a -1. So I think I added instead of subtracting to the y value. It's moving down, so this should have been -8 minus 1. And this other point should have been +8 minus 1. So the resulting points, they should have been, for the first one, it should have been -2, comma, -9. And for the other one, +2, comma, 7. So those will be the correct points. The graph was moving down. I'm sorry about that. But this one on the right is correct. That moved up. So we added to the y. So going back, x cubed minus 1. So we're going to type that. And we do have to type y equals because we want to have 2 variables there. So x cubed, and then I'm going to use the right side arrow of my keyboard to get out of the exponent and then enter the -1. And so you could see here the behavior from the one in red, that is our parent function, and then the one in blue is the transformation that was shifted vertically 1 unit to down, 1 unit down. That's what I should say. Okay, so let's graph one more, and now we're gonna graph the one that had the double shifting. So that was horizontal with the +2 and then a +1 outside. So let's go there, +2 inside parentheses. So I'm gonna enter x +2. You see how I'm included that inside the parentheses. So then I close it. Then I will use the exponent, which, by the way, I'm using Shift 6 to get the caret symbol. And see, if I keep typing there, it's going to look like part of the exponent. So I don't want that. I want to get out of the exponent. So I'm going to use the right side arrow. And then I believe that was a +1 for the vertical shift. So now if we compare, and I'm just going to show you the parent function. So I'm going to eliminate that one for now. And so we have the parent function here in red. And now the one in green is our shifted function, which was 2 units to the left. And you could see here, if we take this origin, this point in the origin, and move 2 units to the left, and then 1 unit up. And I know it looks like it's 2, but here each square is like 2 squares is 1 unit. So let me get a better picture of it. Oh, this is better. So right here we have the point at the origin. You could see at 0, 0. So 2 units to the left. You could see it right here, -2. And then 1 unit up. And you could see that's the 1. We could actually click on it. So it should be at -2, 1. It's a little hard here with this mouse. Okay, so it's almost there. There we go. So we have the point there. And so there you can check your work with your graphing calculator or with Desmos. That's fine with me. Okay. Now the next transformation we're going to talk about is reflection. And we have 2 types of reflections that we will be discussing for this section. One is reflection across the x-axis, and the other one is reflection across the y-axis. And so what happens is that for the reflection across the x-axis, imagine if you have a point here and reflected across the x-axis, the point is now here. So we are going from a point at 1, 1 for the parent function, that's the parent function, and across the x-axis, the point becomes 1, -1. So you could see how the y is the one that changes to its negative sign, or its opposite. So in this case will be the y. So change y to its opposite sign. So meaning that if y was positive here, then it will be negative across the x-axis. And there we have it. Now, if we are reflecting something across the y-axis, then what will be taken, changing, for example, if we take the same point right here at 1, 1, and we reflect that across the y-axis, then the point will be -1, 1. So you could see clearly that what changes is the x coordinate. So change x to its opposite sign, meaning that positive x's will change to negative x's, and the negative x's will change to positive x's. So that is how we work, and because we're changing x, that's why we have the negative sign inside the parentheses. For the x-axis reflection, we're changing y, so remember y and f of x have the same meaning, the output, so that's why we have the negative outside the function. And that is how they will look like. You could see the example here with the parent function being x squared, and then the reflection across the x-axis is right here, and the equation is negative x squared with the negative outside. So it was a reflection across the x-axis. For example 2, we are going to write the equation of the graph. So parent function is x to the 4th power. This is also the parent function of a polynomial of degree 4. And we're going to use that to list the steps of the transformation for g of x and then come up with an equation based on x to the 4th power. So what could we see that the difference will be from g of x and f of x? So g of x, I can see that it is reflected across the x-axis. And also, it's like if we had a parabola upward and now it is downward. So that's also considered the reflection across the x-axis. Also, it is shifted and we're going to say 2 units up. So because it is reflected across the x-axis, we're going to make the y be negative. In other words, we will have negative outside and then f of x from the parent function. Remember, this is a parent function, so if we put a negative in front of it, that's what causes all the points to be reflected across the x-axis. Well, that would be one thing, and this is the equation for g of x. And then also we move 2 units up, so we will put a plus 2. Now, what I'm going to do to write the equation is to use the opposite of f of x, so that will be negative x to the 4th, and then we will have the plus 2 after that. That indicates a vertical shift. If you're not sure, you could always graph them on Desmos or your calculator so you can check your work. Okay, for the next one, we also see a reflection across the x-axis again. And then second, we also see that it was shifted, and we will say 1, 2, 3 units to the right. So because we see to the right, the equation, and in this case we're going to call it h of x, it's going to be the same as f of x, but we're going to include the 3 inside the parentheses. Since it was to the right, remember, we need to think counterintuitively. So we will say minus 3 inside the parentheses, and then we are reflecting it across the x-axis, so all the y's turn to negative, meaning that we will put a negative here. So it will be the opposite. And so the equation for this graph will be the opposite of the parent function, which was negative. And then inside the parentheses, we will have x minus 3 and then to the power 4. So, and you could always check your work. I'm going to just graph it because I don't feel like 100% sure we did this right, but let's check. So I'm going to go to Desmos and I'm going to enter it. By the way, let's go ahead and change this one to the power 4, the parent function. So then I'm just going to get rid of the other 2 graphs and then start with a new one. So this is going to be y equals, and we have a negative outside the parentheses, then we're going to have an x. And we did say that it moved to the right, so that's why we put a minus 3. inside the parentheses because it's a horizontal change. And then we close the parentheses, and then we raised all that to the power of 4. So if we graph that one, and I can't see it, so let's see, and we have here, oh, I'm not showing the parent function. So here in red is the parent function, and then here in purple we could see how it shifted 3 units. You see here from the 0.00 it shifted 3 units to the right, but also the negative outside the parentheses is indicating that reflection across the x-axis. So if you're not 100% sure of your answer, please graph it and before you struggle with your homework and get frustrated. Okay, so we're gonna graph the 3 of them here, the 3 functions that you see. In fact, we're gonna graph the parent function too, which will be the square root function, just the square root of x. So let's see, we're gonna describe the changes that those 3 equations or those 3 functions will have. So first of all, let's revisit the concept of the domain. So we know that the x value need to be positive, so greater than 0, but it could also include 0. So on the function that we have here as g of x, we have the negative outside the square root, meaning that it's going to change y. So we call this a reflection across the x-axis. So let's go ahead and graph them both so you could see the reflection across the x-axis. So I'm going to delete those 2. Here we're going to enter, for the square root, I want to show you something that you could do. You could use your, right here, you see a keyboard. And so if we click on it, we could pull the square root key and then just put an X right there and graph it. So that function will be right here. Okay, I'm going to zoom out a little bit more. Oh, that's a great view. So there we have it. Square root of 4 is 2. Square root of 1 is 1. Square root of 0 is 0. Now, let's get rid of this one here. And now I want to graph the reflection across the x-axis. So we had a negative outside the square root. So I'm going to put a negative and square root, and then we enter x. And so you could see the graph right here. I know it kind of looks like a sideways parabola, which they do exist. But let me change the color here. There we go. So the parent function is here in red, and then the reflection across the x-axis is in blue. So you could see a point here at 1, 1. We have it reflected over here at 1, negative 1. Okay, the next reflection, I'm going to leave the parent function there. So let's go back to our notes. And we have h of x is equal to the square root, and then now we have the negative x inside the square root. So according to our notes, this is going to be a reflection, because the x is the one changing, is going to be a reflection across the y-axis. And so the reflection across the y-axis, so we're going to graph it here on Desmos, and it's going to be y equals, I'm going to use the square root button, and then I'm going to enter negative x. And so that is how the reflection across the y-axis will look like. Red is the graph in red is the parent function, and the graph in black is the transformation. So you could see how the values were reflected across the y-axis or mirrored across the y-axis. So what would happen if we make both negative? Meaning like having both reflections, one across the x-axis and one across the y-axis. And so I'm going to get rid of this one here. And here we have it. So this will be the parent function, which is the one in red. And then the one in blue is a reflection across both the x and the y. And on here, since we're changing both, for example, this point here at 1, 1, I can never get the points to work. Okay, there we go. Okay, that point is going to be reflected across the origin and is now here at -1, -1. Right there. So when you have those two reflections, I guess, yeah, you could call it reflection across the origin. So what would the last one here be? And that is k of x. So we have a negative outside the square root, and then we have a +2 inside the square root. So let's go ahead and graph it. So, oh, I didn't want to get rid of that one. But okay, so we had a negative outside, then we have the square root, and then we're going to have an x +2. So in that case, we could see the graph here in green. So the parent function again is in red. So we went from that to a reflection. Actually, it was shifted to the left by 2 units because we had the +2 inside the square root. And then it was reflected across the x-axis. And so that's why it goes like that. It is decreasing instead of increasing and shifted 2 units to the left. Remember, horizontal shiftings, they look counterintuitive on the equation. Okay, so let's go back to our notes. And one last thing that we had to do here was to determine the domain. They're already written there, but let's just evaluate why. So here we had a reflection. Reflection across the y is changing, so then it will be across the x-axis. And then we also had a horizontal shift of 2 units to the left. That was our transformation. So now for domain, let's start with that last one. And here we have x +2. So what we do is we create an inequality just like this one here. And we say x +2 has to be greater than or equal to 0. And then we solve for x. So x will have to be greater than or equal to -2. If we subtract 2 to both sides, or if we just take the +2 across, goes from adding to subtracting. So this is going to be, the domain will be all the x values starting from -2, that could be the smallest, and then greater than that. How much greater, we don't know, so we use the concept of infinity and then regular parentheses. The one that you see here is the same as the parent function. You could see the domain is the same. And now h of x, for that one, if we take whatever's inside the square root, which is called the radicand, and we say that must be greater than or equal to 0, the way to solve it here is to multiply both sides by -1. And the trick here is that anytime you multiply by a negative number, such as -1, or divide by a negative number, you must reverse the direction of the inequality. So this inequality will actually be reversed, and now we multiply negative times negative, so that will be positive x, and then that will be less than or equal, and here -1 times 0 is just 0. So that's why you could see the inequality symbol reverse. Okay, so we are almost done with this section, and we could do more examples during our live session. So now we completed reflections and shiftings, and those are considered to be the rigid transformations because they do not change the basic shape of the graph. It doesn't alter the way it looks. It will still look the same. It will simply be either reflected or shifted. So they only change the position of the graph, not the shape. Now, the non-rigid transformations are going to be the ones that they cause a distortion and change the shape of the original graph. And so I will show you some examples. But first, well, yeah, let's look at some examples first. So we're going to be using the same parent function, the square root function. And first, let's do a vertical stretch. So I want to put a 2 outside the square root so that what will happen is all of the y values after the square root of x gets calculated, it's going to be multiplied by 2. So what's doing is stretching the graph vertically. So each y coordinate is actually being multiplied by 2. So if you notice at this point, the y coordinate is a 2. On the vertical stretch, that y coordinate, it's a 4. And you could see it clearly here. Now, what would happen if I enter let's say, a 3? So then it's going to stretch it vertically even more. And you could see that behavior right here. So every y value, for example, the parent function, here the y value was a 1. I'm trying to locate that point. Oh my gosh. Okay, and so on the vertical stretch by a factor of 3, that y value is going to be a 3. This is so, there we go. Now the y value is a 3. Okay, now if we choose to multiply by numbers that are smaller than 1, since it's going to multiply every y value, let's use 0.5 times the square root of x. So if we do that, and I'm going to delete the other ones just so that we can compare it to the parent function. So here the one in red is the parent function. The one that you see here, x, the square root of x, and then the one in blue is the transformation, 0.5 times the square root of x. So what did that do? So what happened is that for every y value, after the square root was computed for each x value, we got a y value. In that case, was a 1. And the 0.5 times 1 gives us 0.5, or 1/2. So that y value changed from 1 to 0.5. If we look at the y value here of 2, and we multiply that by 0.5, it will give us a 1. And that happens just for every single point on the graph. So for vertical changes, those will affect the y value. So right there you have the parent function in the middle, the vertical shrinking here in blue and the vertical stretching in red. So let's see how that is generalized into our notes. So it says that for a vertical stretch, that constant will be multiplied outside of the equation of the function. So we'll be multiplying y, not outside the equation, but outside of the parentheses of x. And if that is greater than 1, like the examples that we did with 2 times the square root of x, or 3 times, it was a vertical stretch. And so the key here is always going to be to multiply. Since we're talking about a vertical stretch, we're going to multiply y by the constant. So what happens if the constant is smaller than 1? That's what it says there. But it's still positive, meaning greater than 0. So here we're including numbers from the number line that are, if this was, let's say this was 0 and this was 1, it will be all those numbers in between 1 and 0 without including 1 and 0. So that will cause a vertical shrink. And again, we multiply the y values. That's the example that we did where we enter 0.5 times the square root of x. An example of a vertical stretch, we could use the one that said y equals 2 times the square root of x. In that case, the c value here is a 2, is greater than 1. And here the c value is 0.5, so it's less than 1, but still positive, greater than 0. Now let's see what will happen with the horizontal shrinking and stretching. So just like the shifting, it is going to be counterintuitive as well. So I'm going to get rid of this graphs, but I'm going to leave the parent function there. And maybe this is not such a good example to show you. I'm going to try with this other graph that you will learn in Pre-Cal 2. It's called sine function, and that is the parent function of the sine function. So if I was to do the vertical stretch again, let me show you. 2 times sine of x. You could see how the graph, it is the one in red is the parent function, and the vertical stretch, you could see how it's kind of like being pulled vertically up and also down over here. And if we do the 0.5, or let's say 0.3 sine of x, you could see here that's the graph in black. So from the parent function, you could see how this one is vertically shrunk or compressed. Okay, now let's just delete those temporarily, and now let's see what will happen if we enter y equals. Now I want to show a horizontal stretch, so what I'm going to do is enter the function, and the change, the constant multiplying needs to be happening to the x directly because the horizontal stretching or shrinking. Now if I want to horizontally stretch it, I'm going to think counterintuitively again, and so what I'm going to use is a number that is smaller than 1, and it's going to horizontally stretch it. So you could see that here. Let me change the color of this one. Actually, that's the parent function. I'm going to just change the color quickly. And we could see here, the one in red is the parent function, and the one in purple was horizontally stretched. And that is because I have that 0.5 there. So if I go to my notes, I'm going to see the following. That if I want to horizontally stretch a graph, I will have to use the equation that will have that constant multiplying the x directly, but also it will have to be between 0 and 1. And so I chose 0.5 just for simplicity. But of course, any number in between here, open interval, so parentheses, it will work for a horizontal stretch. Less than 1, but greater than 0. Now let's move on to the horizontal shrinking. So for that, we need a constant greater than 1. So let's see how that will look like with our graph. And so I'm going to enter a constant greater than 1. Let's say y equals sine. And because I want it to be horizontal shrinking, it will be multiplying the x directly. So let's try 4. 4 times x. And I'm going to delete temporarily the 0.5. And so now you have here the parent function is the one in red. And then the one in blue is the horizontal shrunk. And so why is it counterintuitive? So the reason for that is that you don't multiply with like what you do with the vertical stretch. Instead, you are going to divide. Divide every x, in this case, by c. And how do you know if it's a horizontal or a vertical stretch or shrinking? Depending on where the constant is located, the constant that's multiplying the function or the x value is located at. So if it's outside the parentheses that goes with the x, the change happens to the y. Therefore, we multiply c times y. If the change happens directly to the x, we divide every x by the constant. And of course, you could always check your work with your graphing calculator or with Desmos. So we're going to graph those two on Desmos, and that will be the last problem, but then we're going to write something else. So I'm going to get rid of all these functions here, and just to remind ourselves of the absolute value that looks like a V shape. So again, if you click on this keyboard, you will see more functions appear. And so I clicked on that one for absolute value. I'm going to just enter that and then use it again. Okay, that's the absolute value function. And the first example that we need to graph is 3 outside the absolute value. So we're going to enter y equals to 3. And then the absolute value of x. Okay, and you could see how the 3 stretched the parent function vertically. I know it looks like it got narrower, but which could be mistaken by a horizontal shrinking. But because the constant is outside the absolute value, I know the change didn't take place on the x directly. It took place after the absolute value was calculated. So if the change happens to the y, it is going to be a vertical change. And in this case, it's a vertical stretch. Now, the other example that we have here in our notes, we have a 1/3. So we're going to enter, y equals, I'm going to enter the fraction in parentheses, 1/3. And then, actually, I don't need that. I'm just going to use the arrow to get out of there. And then I'm going to select the absolute value, x absolute value. Oh, I didn't enter anything there. There we go. So I'm going to delete this temporarily. So that 1/3, what it's doing is a vertical compression. Imagine like this was a balloon and you are holding it with your 2 hands by the y-axis, and then you squish on it. So it's going to be compressed vertically, but if you have water in your balloon, perhaps it's going to expand horizontally. So don't be confused after you graph it. Even if you think that it is stretching it horizontally, you need to look at your notes and notice that the 1/3 is outside the absolute value. Therefore, it is a vertical change to the graph. Okay, and let's graph one that will look like a horizontal one, like right there. And so if we graph that, with a 3 inside, it actually happens to look like the one we had here. And they do. They're overlapping, I believe. Yes, they are overlapping. So in this case, and this does not always happen, okay? I guess we could consider by how they have the same shape. But how do we know which one is a horizontal and which one is a vertical? By where the 3 is located. So here is outside is vertical stretch by a factor of 3. Here the 3 is inside the absolute value, so it is a horizontal shrunk by a factor of 3 because we divide every x by 3. Now, just to finish, I want to warn you that sometimes you might have multiple transformations. You might have something like, I don't know, a vertical stretch, and then a horizontal shift, and then a, I don't know, a vertical shift. So the steps that you must take to solve this will be, first, you need to take care of your horizontal shifting. Oh, and then let's put a negative there for fun too. Horizontal shift, which will be, is the one being represented by the +2. Second, you will take care of your stretching or shrinking. And that will be given by the 3 right here. Not the negative, just the 3. And then third, you will have to take care of your reflecting, whether it's across the x or the y-axis, reflecting. How do we know how are we reflecting? Well, that is given by this negative sign right here. And that will be a reflection across the, since the y is changing, it will be across the x-axis. So it will be like a downside V. And then fourth, at the very end, you are going to look at your vertical shifting. So if you're doing your homework and you're not getting the same graph as the calculator or as your decimals, then it's probably because you're not following the steps of the graph, of the transformation. So make sure you write this down, and that's it. So thank you for watching.